Assalamu alaikum and a very good day to everyone. I hope you are all doing well. Okay, so today we are going to go to the circuit application in Laplace transform. Okay, so for in the beginning, I will just want to show you the basic of calculating voltage. We have V equals to IR. And if we represent it in a circuit form, it will be like this, where resistor with the current going that way, and then we have V. Okay, now where's the V? Yes, there goes the V. Alright. Okay, so taking the Laplace transform to the V equals to IR and also to the circuit. So basically we have to transform all to Laplace transform. Therefore, we will get V as equals to R I S. Okay, so it's nothing really. Basically, in Laplace transform, if we have like a constant, basically there will just be an additional of s right after the constant. And therefore, because of the similarities, I mean no changes of value before and after, or I can say during time domain and also the frequency domain, which is in Laplace transform, the circuit will be similar. Alright, next we are going to do inductor. Basically, as we all know, usually in a circuit we have three basic components, which is the resistor, inductor, and also capacitor. So for this one, I will show you the example of the inductor, because basically in the circuit application in Laplace transform, we have to transform all the circuits given into a Laplace transform circuit. Okay, so for example, if you have an inductor, okay, basically the basic circuit will look like that. And for inductor, V is equals to L integration of the current, which is the I dt. So again, we will do the Laplace transform to both of the components, which is the circuits and also the equations. Okay, taking Laplace transform for both sides. I'm sorry if there's like a lag in the video, because for this video I'm doing a voiceover video. Yeah. Alright, so basically once we have take the Laplace transform for the V in time domain, we will get Vs equals to L as Is minus current 0 naught. Okay, so actually the basic idea is that if you refer to the appendix table that we have for the Laplace transform, if we have the differentiation, we will basically get the output like that. Okay, so we arrange, once we have got the value, we will arrange it, and that's why after we rearrange it, we will become Vs equals to S Lis minus Li 0 naught. Okay, then again, actually we have to transform the circuit into a Laplace transform circuit, and here we will get the circuit as shown. Okay, again, from the original circuit, the current is going this way, with the inductance as L, referring to the equation again. Okay, and then now we are left with the voltage Li 0 naught. And actually that's all. Again, I have to remind all of you the voltage drop are all the same for all of the components from resistor, inductor and also to the capacitance. So actually, if we do the KVL for the circuit, we will actually get the equation of to get this equation, right? Okay, so if you see here, we have negative LIO naught, and that's why if you see in the table, the negative value is above, while the positive value is below for the power supply. Alright, next. So you already have done it in terms of voltage. Now you can do it in terms of the current. Well, basically in terms of the current, it's just that you arrange the equation that you have found before to a current term. That's all. And when you have arranged it, you will get something like this, where you will represent this. If you present this in a circuit, you will get something as shown. Okay, the current is going this way, and after that we will have yes, the current of IO naught over S, and also the inductance of SL. Okay, I just want to remind to all of you that basically if we want to find the current, the it is good, the circuit will be in parallel form, while if you want to find it in a voltage, if you want to find voltage, the circuit will be in a series form. Alright, that's done for the inductor. Now we are going to move forward to the capacitor. Alright, I will start by drawing the basic circuit of the capacitor. Again, all will be similar with the basic components of voltage, current, and also the component itself. So for capacitor, we know that I equals to C, the derivative of the voltage, which is dV over dt. And again, taking the Laplace for both the circuit and also the equation. In my video here, I'll try to do as slow as I can. Therefore, I really hope that all of you will somehow understand the flow, because I think basically the flow is very straightforward. Okay, so again, how do I get the value inside the bracket is from the Laplace transform of differentiation. And then after that, I will rearrange the equation until I obtain something like that, and then I will present it in a circuit form, which again, as I said before, if finding a current, the circuit will be in a parallel form. Okay, the current there is CV 0 naught. And here I realized that I or I can say I forgot to put C in the equation. So silly me, I'm so sorry. Alright, so again, the current going this way. Then we have the 1 over CS there, and then again the voltage drop, which is equal to all of the circuits that we have, I have shown today. So the rule is easy, where the circuits, the voltage will be the same for all of the circuits. Okay, next I'm going to explain to you in terms of voltage. So repeating the previous method is just that by rearranging the equation that you have before in the current term, you will get Vs equal to 1 over Sc Is plus V0 naught over S. And again, for voltage, we are going to represent it in a series circuit. So the inductance is what, oh my god, I think I have been using wrong term, not inductance but capacitance is 1 over Sc. And yeah, I just want to highlight here again, why do I use positive and minus there? Because we have the value of positive in the original equation, that's why I put positive and negative, while we have negative there, that's why the arrow is going up, which is the opposite of the current. As simple as that. Alright, so basically I hope you do have the idea now. So actually there is this one condition that you have to well, I can say you have to know this in order for you to somehow ease your way in your calculation. Okay, so there is a condition that we can call a zero initial condition, or sometimes in the question the term that will you be used is zero initial value. So for example, if given the initial zero initial value, what will happen is actually the current in your inductor will be 0, while in the capacitor the voltage will be 0. So what actually happened, let us see. So for example, in this, okay, if you see just now for the capacitor, yeah, as I show here, the voltage will be 0. So imagine replacing all the 0 into any V. So you will see the result will be 0, so automatically this will be removed. Okay, so the circuit will be simpler, and also same goes to the inductor. Okay, because if that component is removed, overall will be simpler. Okay, so that's all, and all the best. Assalamualaikum.